Your next step will be perform a summary analysis on selected parts below. So I'm going to go ahead and click that box there. Okay, so it's completed here. It says summary analysis complete. Now simply scroll down and select one device using radio buttons for each section. Click that off here. So in the first case, I only selected a power module because it was the only part that was schematic enabled. So it's showing me what its efficiency curve is across the from 0 to 19.6 amps, what we had entered as our max current. It's also showing what the power dissipation would be, and it's giving an estimation of the die junction temperature. The die ambient can be helpful in overall looking at the system and possibly having to derate current on outputs. What we have up here at the top, you see ambient temperature range. It's set to 25 degrees C currently. We can adjust this for the overall system, and we can look at the junction temperatures for all of the different output rails. So therefore you can look across your full spectrum of temperature range of your application and kind of get an idea if you might be getting into a condition where you might have to derate the output current on a device. So that is helpful there, and we'll show that here in a minute more after I select some devices. So to begin with, I'll just go down through the list of the different rails. This is a core 1.5. Here's the one device that we selected for looking at. Well, we didn't select any other devices for comparison, so that's the only option I have to select. So I'm going to go ahead and select it. When I select it, you'll see up here at the top, it starts to show some details about it. Its light load efficiency and typical load efficiency, its max load efficiency, and its junction temperature max. This junction temperature max is affected by what the ambient temperature here is set at. So I'm going to go down through the list and select devices. So in this case, also behind part numbers you'll see a bracket, an S or a D. That is for a single output device or a dual output device. So in this case, we selected some different options. We selected some single devices to look at and some dual output device that could service two rails. So in this case, I'm going to go ahead and select the dual output device, the 85033. And you'll notice when I select it, it comes up here as it's a dual output. It's only half of the solution. So what I'd come down into the next rail that was also the 85033 was suggested as the secondary rail, and I would select it as well. If you don't select, when you're dealing with dual output devices, you need to select it for both rails, otherwise the system will give you an error when you try to generate schematic and make you correct it. We'll go down to the next rail, and you can see the difference. You can look at power dissipation, and you can look at the overall efficiency of the system changes as the two different parts you're looking at here. So in this case, the 85033 is a much better across the efficiency range of my 0 to 2 amps. It looks much more efficient, especially at the low end here. So I'm going to go ahead and go with that device over the power module. However, if you needed an all module solution, then you could go with the module as well for simplicity. As far as the linear regulators, they're all linear, so basically it just comes down to power dissipation. Some of the package have a little bit better theta JA. In this case, there's not a lot of difference in the power dissipation for the linears. So I'm just going to select one of them here for my summary. So that was my last rail. There are sections for the other unused rails, but we don't have any parts to look at, so we don't have to select any there. Only the rails that we were using in our system. So once I've completed that, I have a summary up here of all the devices I selected, their light load, typical load, max load efficiency. There's some numbers here, the light load, max load, and typical load efficiencies, as well as a maximum power dissipation, along with some graphs up here that you can look at. Once you have your system all selected, you can look at the ambient temperature and how it affects your junction temperatures. You can see right now most of them are in the green. The core 1.5, which is the highest current one, which is a 2-module solution in a current share configuration, is your highest. Each device running about 67 degrees. You can start increasing your ambient temperature and see how that affects temperature of your junction. So you can see once we get up to 65 or so, we're starting to get a little high on the junction temperature for the module. It's not to the point yet where it would derate current, but typically around 115 we start to warn people that it's possible that you're going to start derating your output current there, because you're getting close to the junction temperatures of the device. Typically are about 125. So as you can see, once we hit 115, a message pops up here. It says warning, high junction temperatures may derate output current. So once you're satisfied with your design that you've done and you have all your rails selected, it does give you some cost for the base silicon cost. It doesn't give the additional information yet, but we will be adding possibly the BOM total cost and hopefully the footprint as well in future version of this tool. So the next step would be to generate a reference design.